The goal of today's lesson is to solve equations that have multiple variables in them. And we're not solving to come up with a specific numerical answer, but we are trying to solve for a variable to manipulate it to get it into terms of the other variables. So if we take a look at the do now and just quickly go through solving each of these. I'm going to solve each of these linear equations, and they're meant to be pretty straightforward in terms of what their answers are, because it's not solving the equation that's the point. The point is to see what's happening here. What you can see about the structure is that both 1 and 2 are in the form ax minus b equals c, where a, b, and c are each some distinct numbers. And I can create any number of similar examples to what's up there. So I can create 3x plus 6 equals 12. Or actually, I should make that a minus, even though they're interchangeable. But 3x minus 6 equals 12, just to be consistent. Now, how would I solve 3x minus 6 equals 12? Well, I would add 16 to both sides of the equation, and then I would divide each side by 3. Okay? The whole point of that exercise is to get you to see that if you are then asked to solve an equation that does not have any numerical representations or has many different variables, you're going to follow the same steps. So hopefully you would recognize that I'm trying to isolate the x here, so that in order to do so, I would add b to both sides. So I would get ax equals c plus b. And that didn't come out too clean, so just want to make sure you see that it's c plus b. Those look like an a. You should hopefully realize that c and b are not like terms, so that they cannot be combined. And now to get x by itself, I would divide each side by a, so that x is equal to c plus b divided by a. That's the goal of today's lesson. So let's go through some examples. I want to solve ax minus b equals c for b. I can approach this a couple of different ways, and I'm going to show you each of the two ways to approach it. I'll divide it in two. Approach 1 is to add b to both sides, so that I get ax equals c plus b, and then subtract c from both sides, so that I get ax minus c equals b. Perfectly valid way to do it. Now, somebody might see this a little differently. They might say, I don't like to move the variable that I'm solving for, i.e. the b, so I'm going to move the ax by subtracting ax. Now, where you have to be careful is it's a negative b is equal to c minus ax. Well, negative b is not a valid answer yet. When you're solving for a variable, it has to be a positive. So how do I change all of this? I just multiply everything by -1. So now I get b equals negative c plus ax. Well, are these two answers the same? Definitely. Why? The commutative property of addition. Next example, a times x plus b is equal to c. And I'm asking you to solve for a. Now, a natural inclination would be to distribute the a to the x and the b. The problem is my answer should have only one a at the end, and if I were to distribute the a, I'd get two a's. I'd get ax plus ab. I don't want to create more variables if I can avoid it. So I can simply cut to the chase and divide both sides by x plus b. And now I'm done. The way to think of it is x plus b is being multiplied by a. How do I undo multiplication, or what's the inverse operation? I can divide. Let's continue on. Similar example, except I want to solve for x. Again, a natural inclination might be to distribute the A. But I'd rather try to avoid doing that step. So what I'm going to do here is I'm going to divide by the A to get x plus b equals c over a. And now all I have to do is subtract b, and I get x is c over a minus b. Could you have taken the first step of distributing the a? Yes, but you create more work when you do that. And then the final one of these types of examples, ax plus b equals d minus cx. Now, if you visualize this as very similar to a question like the following: 5x plus 8 equals 10 minus 3x. Okay? What I would suggest you would do here first is collect all the x's to one side. Try to keep them positive, not necessary, by adding 3x. Well, if you then take that and transpose the concept over to here, what do you want to do? And let me just erase this so we have some room. You want to add cx to both sides. The thing is, since I have an a and a c, I can't put the two of them together because they're different variables. I don't know what they are. I'm a little closer to home because I've collected all my x's to one side. Get the b out of there. Now, the x is showing up in two places. We've previously done lessons on factoring, or as one of my students called it, backwards distributing. Whatever gets you to understand, it's fine by me. How would I factor here? Well, hopefully you'll see that x is the GCF, so that I can factor out an x. And now I have a problem similar to one of the earlier ones, where all I need to do is divide. So what is the final answer? X equals d minus b over a plus c. Now, to show you a little bit more of a practical use of this concept, and we want to go that way. The formula A equals P plus PRT is the formula used to determine how much money you would get in a certain future time if you deposited a fixed amount today at a certain rate for a fixed period of time. It's called simple interest as opposed to compound interest, and I don't want to make things more difficult than they are. Let's just focus on this formula. So I have the formula A equals P plus PRT. So the way this formula is set up, it's set up or designed to tell me how much money I'll have at some future date if I know how much I'm going to put in today. I want to solve for P. Well, this is similar to the problem we just worked on in that P shows up in more than one place. So what do I want to do? Factor out a P. I'm going to write this over here, but please remember that inside the parenthesis should go the result of dividing by P. Common mistake students make is they don't realize P over P is 1 plus, then I have to tack on the RT part. Or, said another way, the result of distributing here has to equal what was right above it. Now, my last step, I divide by 1 plus RT to get my formula. Now, why is that such a relevant change to the formula? Well, let's look at the next example. Let's say I'm not so concerned with how much money I'm putting away today. I want to know how much money I need in the future because I'm going to buy a car a couple of years from now, or your parents are saving for college education, or to put a down payment on a house, or whatever it is. So I want to know what I need to have, and what I need to put down today so that I have $5,000 3 years from now. So what by manipulating this formula, what it does for me is it gets all of the number parts on the same side because I'm trying to figure out what P is when I know A, R, 2% is written as 0.02, and I know T of 3. This is much easier to work with than if I try to solve this by saying 5,000 equals P plus P times 0.02 times 3. That's a little bit of a mess. Okay? So this is all just now math. And if you work out those numbers, you'd get $4,716.98. So what this is telling you is if you put aside today $4,716.98 at 2%, for 3 years, you'll have $5,000 simple interest. Okay. A couple of other examples. The formula for kinetic energy, K, is it equals 1/2 times the mass velocity squared. Okay? And I want to solve for velocity. So I need to get rid of anything that's attached to the V. The first thing that's attached is a half. How do I get rid of that? Multiply by 2. 2 times a half is 1. So it leaves me with mv squared. What's still attached to the V? M. By what operation? Multiplication. How do I undo that? Inverse operation of division. Now, I still haven't gotten V by itself. I've got V squared. A natural inclination is for students to say, well, let me divide by V, because V squared divided by V is V. The problem is if you divide both sides by V, you're still left with V on the left side. All right? You're dividing a fraction by V. So that doesn't really help you. So I need to think of a way to go from V squared to V. How do I do that? Take the square root. If I do it to one side, I need to do it to the other. What's the square root of V? V, because V times V is V squared. Now, the other thing that will trip students up. If I gave you the simple, and I'm going to show you this example over here, x squared equals 16. Hopefully you would know that the way we were taught to solve this is set it equal to 0, because it's quadratic, factor, using dots, and I get my two answers of 4 and -4. There really is a shortcut, and the shortcut is I could have taken the square root of each. However, you have to realize that not only is it a positive, but a negative works, because positive times a positive is a positive, and a negative times a negative is a positive. So when I write my answer for kinetic energy, it's not only the positive of 2k over m, but it's the negative of that. Because either way, when I multiply by the same sign, I get back to a positive answer. All right, last two examples. We have a little bit of a difference here now because I have fractions, the bane of students in math. I don't like to deal with solving equations with fractions, so I want to get rid of them. You should recall that we dealt with that by using what's called the LCD, or least common denominator. Well, what's the least common denominator of 6 and 7? 42. So I'm going to multiply all three terms by 42. In other words, 42 times x over 7. 42 times, x over 6. All of you at home yelling, he made a mistake. Good. Hopefully you saw that. Times y over 7. And then 42 times a over b. I have to multiply it by each of the separate terms, otherwise my equation doesn't stay balanced. Well, this becomes 7x, cross cancel. This becomes 6y, and this becomes 42ab. Well, what was I solving for? X. Add 6y. What's still there? A 7. I divide everything by 7. I can simplify this. Sorry, that should be a 40. Try not to get it. 42AB. I can divide 7 into the 42 and get 6AB. I can't divide 7 into 6, so it stays 6y over 7. Either of those two ways are acceptable to me, although on a multiple choice you would see it written this way, its simplest form. Now, similarly, in number 14, I have fractions. But my denominator are b and d. Well, I don't really know what the least common denominator of b and d is numerically, because they're obviously variables. But there's always a foolproof way to come up with a common denominator. It may not be the least, but it'll be common. You just multiply the denominators. Well, what are my denominators here? B, D. So the way to view it, I'm doing BD times AX over B, BD times CX over D, and BD times E. My common factors cancel, so what am I left with? DAX plus BCX equals BDE. Now, looks like a mess. Somewhat. How many times does X show up in my equation on the left side? Twice. So what does that mean I can do with the X? Factor. I factor out an X, DA plus BC, and then I divide. Okay? So, what was the purpose of the lesson today? The purpose of the lesson was to solve equations that have multiple different variables in them for one of the variables. Hopefully you'll realize that you're going to follow the exact same steps to solve it as if you were solving any regular equation. Okay? You're going to use your properties of equality, of multiplying, dividing, adding, or subtracting, and sometimes even factoring to do so.